I would like to welcome you to the Mathematics of Design. I am Professor Jay Kapraff, and with me today are three students, Wei Li, Maria Ramirez, and Howard Tews. Now, where do mathematical ideas come from? They can come from anywhere, although most people imagine that physical sciences and astronomy are the primary sources. Mathematical ideas can just as well arise from music, art, or architecture. The first expression of these ideas is in the form of geometry, the most basic branch of mathematics, since it defines our notions of space. In school, artificial barriers are erected between subject areas such as art, music, architecture, mathematics, chemistry, biology, and physics. In fact, all of these disciplines are related to each other, and it is my feeling that geometry serves as a common language spanning them all. In these lectures, we shall try to break down the barriers separating disciplines and show how geometry lies at the foundation of them all. That is not to say by using geometry alone, a beautiful building can be built, a work of art created, or a symphony written, or a new chemical compound derived. Even though the musical scale can be related to the mathematics of frequency intervals, and number series derived from the length of a vibrating string, and chemical compounds can be related to geometrical structures called polyhedra, and crystals, the creativity and imagination of the composer or chemist is necessary. Mathematics serves only as a tool. The same holds for other areas of mathematical applications. On the other hand, without mathematical constraints, such as the musical scale or the limited possibilities of crystal structures, uninteresting sounds, but no music would be created, and there would be no basis to create new chemical compounds. The same holds for spatial design. Without constraints based on the geometry of space, a design will have no form or structure and be without interest. Einstein had this to say about the relationship between the artist and the scientist. Where the world ceases to be the scene of our personal hopes and wishes, where we face it as free beings, admiring, asking, and observing, there we enter the realm of art and science. If what is seen and experienced is communicated in the language of logic, we are engaged in science. If it is communicated through forms whose connections are not accessible to the conscious mind, but are recognized intuitively as meaningful, then we are engaged in art. Common to both is a loving devotion to that which transcends personal concerns and volition. These lectures will show how math can supply interesting constraints on spatial design and result in new ideas to create designs that you might not have been aware of. You, in turn, will be asked to carry out a series of design projects. We will also show how the same math that results in interesting spatial designs also constrains the hand of nature and lies at the foundation of designs in nature. I have brought with me several examples of geometrical structures that are found in nature. Here we see a beehive and a froth of soap bubbles and a pattern of spirals on the surface of a sunflower. Here we have a bunch of garnet crystals. Now I'd like to introduce you to a very old puzzle called Tangrams. Tangrams is an ancient Chinese puzzle made up of pieces that come from this dissection of a square into 7 polygons. You will notice that there are 5 45-degree right triangles, a square, and a parallelogram. The object of the puzzle is to create various pictograms, such as the one shown on this sheet. You must create these pictograms using all 7 pieces, with no repeats. Now, the earliest reference to tangrams was in a Chinese book dated from 1813. Tangrams were the Rubik's Cube of the 19th century due to its popularity in those days. Now, I would like you to cut out the tangram pieces from this sheet. I would like you to try to assemble the pictograms that are shown in this figure. Now, it's a real challenge to construct Lloyd's Indian and squaw, which are down below. Now, Lloyd wrote a purported history of tangrams in the 19th century called the 8th Book of Tan, which turned out to be a practical joke. Now, if you're successful in making these patterns, then I would like you to try to recreate the original square from which the tangram pieces came, and then to create a rectangle and a triangle from using all 7 pieces. So you can begin to cut out your tangram pieces right now. Okay, as you see, Wei Li is beginning to assemble the pictogram of Lloyd's squaw. She's using all 7 pieces from the tangram puzzle, and she's going to be using these pieces only once with no repeats. And I think that she's got it. Thank you very much. Now I'd like to show you something about the geometry of these tangram pieces. And I have a little diagram here to show you that pretty much tells the story. Now, what do you notice about the tangram pieces in this diagram?
I can see that there are 2 similar triangles, and it forms a square and a parallelogram.
Yes. Anything else?
I think that the 3 triangles are the same, but in different sizes.
Yes. How many different sizes?
3.
3 different sizes, correct. Howard?
I noticed that the hypotenuse of the small triangle is the side of the larger side. I guess that's why they all fit together.
Yeah. Very good. Very good. Now I'd like to change the subject just slightly